Okay, quick bit of practice here before we get you calculating hydroxide concentrations. There might be really awesome data books out there that give acid and base constants for every substance, but they decided to save ink and space in the Alberta Ed book and only give acid constants. So if you want to work with fluoride ions acting as a base, you will find them in the acid-base table, but you're going to find a row that looks like this. And that row shows that hydrofluoric acid can give away a hydrogen, and when it does, it turns into fluoride ion, which is a base and could maybe take back that hydrogen. These two are what's called a conjugate pair. They're like the before and after pictures of the same substance. And they tell us when this thing is behaving like an acid, its acid constant is 6.3 times 10 to the minus 4. Chemistry kind of has a pro-acid bias. We almost always talk more about acids, work more with pHs than POHs, and in this case, we give acid information and not base information. If you want the base constant for this, if you're interested in fluoride taking a hydrogen instead of HF giving one away, then, according to our formula here, the base constant you crave will be the ion product for water, which is 1 times 10 to the minus 14, divided by your acid constant, 6.3 times 10 to the minus 4. And when you put that in, 1 times 10 to the minus 14 divided by 6.3 times 10 to the minus 4, you should get 1.587. That's too many sig digs, but just so you can check your work, times 10 to the minus 11 for the base constant. If you got 1.587 times 10 to the minus, what would it be, 19? Your problem is with scientific notation down here, and the fix for you would be either to use the scientific notation key on your calculator, or what might be simpler, bracket this number. Okay? So if you got this but with the wrong exponent, please bracket this, run it again, make sure you can get this. The Unit 4 exam will rough you up if you're making this mistake, because we do this a fair bit. So if you got 1.587 times 10 to the minus 11, wunderbar, everything's working fine. And I should mention, because this acid constant had 2 sig digs, we should trim this to 1.6 if we were giving an official answer. HSO3 ions are next. Now, be careful with this one. There are 2 rows of the acid base table that talk about this. The first row is H2SO3 turning into HSO3 minus. There's another row where HSO3 turns into SO3 2 minus, the sulfite ion. Which one do we want? It's not this one. In this row, HSO3 is giving away a hydrogen, turning into sulfite. That means it's acting as an acid. That is not what we're after here. We want to see it acting as a base, like here. In this row, HSO3 would take a hydrogen and convert to sulfurous acid. This is the row you need, and that means the acid constant we're talking about is H2SO3's, which is 1.4 times 10 to the minus 2. Ka equals 1.4 times 10 to the minus 2. So the base constant is, just run your formula, 1 times 10 to the minus 14 divided by 1.4 times 10 to the minus 2 gives 1.4 times 10 to the minus 2, 7.1 times 10 to the minus 13. Back, sorry. 0.1 times 10 minus 13. There we are. As you might have noticed with, just from the equation, the bigger your acid constant is, the lower your base constant comes out. This one had HF had a kind of high acid constant, and so it came out with a kind of low base constant. HSO, H2SO3 has a very high acid constant. This is about as high as they get on our table, and that means it has a very low base constant. This is a theme you'll see over and over where if you're very good at being an acid, you're very bad at being a base and vice versa. Being better at one of these things makes you worse at the other one. So when you see a high Ka like this, only a -2, you're thinking this Kb is going to be very low, like -13. Hope that makes some sense. Let's see if we can do one more of these. A 0.220 mole per liter solution of NH3. Okay. Oops, sorry. Before I get into that, the row we're looking for on the acid-base table shows ammonium as the acid and ammonia is its conjugate base. So the acid constant for ammonium is 5.6 times 10 to the minus 10. 5.6 times 10 to the minus 10. And our base constant is the ion product for water, or the autoionization constant for water, the dissociation constant for water. That thing has too many names. 1 times 10 to the minus 14 divided by 5.6 times 10 to the minus 10. But wait, they gave us a concentration here. How do we use this? Trick question. We didn't need that at all for A and B, did we? This is fluff. They threw that in there to see if you would tie yourself in knots trying to incorporate it somehow. The strength of an acid doesn't care about how high its concentration is. Those are different things. So if you ignored that number, good for you. If you tried to include that number, you probably should have thought, wait a minute, why didn't they give me concentrations here? I did A and B without concentrations and I was fine. Let's see if I can do C without a concentration, and it would have worked. Okay, so 1 times 10 to the minus 14 divided by 5.6 times 10 to the minus 10 gives 1.8 to 2 sig digs times 10 to the minus 5. Acid and base constants don't have any units, so that should be all we need there. Good. Now that we have this, I betcha the next exercise is going to be use base constants to find some OH concentrations, which is a bit of a chore, but we're chemists, we love it. See you there.